A microwave oven is a metal box that emits powerful waves to heat or cook our food. The metal construction contains these powerful waves that can harm our bodies. But one side of this metal box is sealed with a glass door. How can that prevent the radiation? Well, when we look inside the microwave oven, we see that there is a metal mesh behind the glass. From the perspective of light waves, there are holes in that mesh allowing them to easily pass through, which is the reason we can see inside the microwave oven. But when microwaves try to escape, they encounter a barrier. From the perspective of microwaves, there are no such holes which prevent the waves from exiting the microwave. Therefore, to microwaves, that mesh acts like a solid metal barrier. This technique, which is called the Faraday's cage, blocks the certain waves from getting out or coming in. To understand this, we should consider the wavelengths and the size of a mesh hole. The wavelength is the distance between two peaks or valleys of the wave, which can be calculated by dividing the speed of light by the frequency of the wave resonance. The microwave oven operates at 2.45 GHz, which corresponds to a wavelength of 12.2 centimeters or 4.8 inches. On the other hand, the longest wavelength in visible light is 750 nanometers, which we perceive as red color. The wavelength of microwaves is at least 160,000 times larger than the wavelength of visible light. This comparison is like comparing the size of a sand grain to that of a large airplane. Now, one can assume that a grain of sand can pass through the mesh easily, but a big plane definitely cannot. The microwave oven operates at 2.45 GHz, which means the waves resonance 2.45 billion times in a second. So how this process can help heat the food? Usually, a significant portion of the foods we heat in the microwave oven contains water. Water has polar molecules which can be considered as dipoles, similar to magnets. When water molecules are affected by a strong electromagnetic field, they become oriented along the field, and as the field rotates, the molecules rotate accordingly. As all the tiny polar molecules inside the water rotate, they rub against each other, leading to frictional heating, which can be then transferred through the rest of the food. So in this way, the type of the heating that microwave and conventional oven create is different. In the microwave oven, the food is heated from the inside, and then the heat reaches the outer layer of the food, so the food is heated from the inside to the outside. But in the conventional oven, when the heater or flames heats up, the heat reaches the outer layer of the food through the air and warms it. Gradually, this heat penetrates into the inner layer of the food, so unlike microwave oven, food is heated from the outside to the inside. It is true that microwaves target the water molecules in food. However, when we put a glass of water and an ice cube together in a microwave oven, we observe that after some time, the water heats up and starts boiling, but nothing happens to the ice. The reason for this is that water molecules can move or oscillate freely in a liquid state, but in the solid state, the same molecules form a structure that cannot move freely anymore. Therefore, they are not affected by the waves. Since electromagnetic waves cannot melt ice quickly, the microwave oven defrosts with less power over a longer period of time. Do microwave ovens really cook from the center? To find the answer, we should know how far the electromagnetic wave can penetrate inside the food, which brings us to a concept known as a penetration depth or a skin depth, indicating the depth at which the wave reaches 37% of its initial value. The penetration depth depends on the dielectric property and the conductivity of the food, and also the frequency of the wave through the angular frequency. By knowing all three of these variables, we can calculate the penetration depths of the waves into any material. For example, for a potato, based on these variables, the penetration depth is assessed to be 1.8 centimeters. In this case, for a typical size of potato, the waves cannot heat it from the center, which is usually the case for other types of food. If you are interested, here are the penetration depths of different foods. As we can see, water has the greatest penetration depths among them. Do microwave ovens alter the structure of food? For the answer, we should look at the electromagnetic spectrum. This spectrum is divided into two sections, non-ionizing and ionizing waves. The microwave oven operates in the non-ionizing region, so it cannot alter the food structure. Non-ionizing waves do not carry enough energy to ionize atoms or molecules. On the other hand, ionized waves like X-rays can completely remove an electron from an atom or molecule. While it cannot destroy the food structure, it can result in food having both a dry and moist texture simultaneously. In a conventional oven, when heat reaches the center of the food, water droplets migrate to the surface, where it is much hotter than the center, so they then turn into the steam and escape from the food. However, in a microwave oven, water droplets are heated and begin to escape from the center. When they reach the surface, since the surface temperature is lower than the center of the food, they do not turn into steam, but instead collect there. That's why heating food in a microwave can result in a food being very dry on the inside while the surface becomes more moist. You might be surprised to learn that the heating efficiency in a microwave oven relies on the length of the cavity. Let's consider the wave inside the longer cavity. This is the incident wave, this is a reflected wave, and this is a reflection of the reflected wave. First, let's see how these reflected waves are obtained. For this, we can assume that there is no wall that the wave hits. The reflected wave can be considered from the point where the wall is placed. By flipping the wave, we can understand how the reflected wave forms. The same approach can be followed for the reflection from the other side of the cavity. As these waves travel, they combine to form the composition of waves inside the microwave oven. But how can we form a combined wave more efficiently? By choosing the right length of the cavity, we can align the third reflection with the incident wave. In this case, the combination of the wave forms a particular wave called a standing wave. This length is a factor of half a wavelength. In typical domestic microwave ovens, the length of the cavity is around 30 centimeters. As can be observed in standing waves, there are points at which the electromagnetic waves are zero, meaning there is no interaction with food, resulting in cold region. Conversely, where there are more oscillations resulting in hot regions. The use of a standing wave results in non-uniforming heating. In microwaves, a rotating tray is used to distribute heat more evenly by rotating the food, which helps improve conditions. However, uniform heating is still a challenge to achieve. If you're enjoying the video so far, please consider liking the video. To achieve uniform heating, the heating elements used in conventional ovens can be incorporated into microwave ovens. Typically, there is a grill stand equipped with these elements where you position the food to allow it to be heated from both the inside and above. This mode is referred to as a combined mode or in some devices grill mode. But where do these waves come from? The waves are guided through the waveguide. Waveguide is a metal tube which can guide and handle high-power waves. The waves, which are generated by the magnetron, travel through the waveguide to reach the food. The magnetron, which is the heart of the microwave oven, has to produce wave at 2.45 GHz. However, sometimes it fails to be accurate. This flaw makes the magnetron unreliable. This inconsistency is also seen in the emitted power. The magnetron was used in early radar systems in World War II and subsequently in microwave ovens. However, the magnetron soon lost its place in radar systems due to its unreliability but is still used in microwave oven. Beside the magnetron, there are only three main components in microwave oven: high voltage transformer, high voltage capacitor, high voltage diode. The transformer boosts the voltage to 2 to 3 kV to power the magnetron, which is both powerful and dangerous. But how all of these electronics are safe when there are high power waves inside the microwave? When there is food inside the microwave, most of the wave energy is absorbed by the food. However, when the microwave is empty, this energy can potentially damage the electronic equipment of the microwave oven. So try to avoid operating the microwave oven when it's empty. Well, the primary concern is how we can be affected by radiation leakage, given the presence of high power waves inside the microwave oven. The FDA has taken steps to address this concern for us. The FDA has regulated manufacturers since 1971 and requires them to obtain a certificate for health safety, ensuring us that it is safe to use the microwave ovens. But it is important to understand how they consider the health hazard. The parameters they consider for that is the power density, which is the amount of power radiated toward humans in a square centimeters. The limitation indicates that if the power density of a microwave oven is below 5 milliwatts per square centimeter at 2 inches from the surface, it is considered safe to use. As the wave decays exponentially with distance, being 10 times weaker every 10 times the distance, the radiation becomes significantly weaker with increasing distance. So as long as you don't rub your face on the door when it's operating, there is no need to worry. But the only thing you should worry about is don't operate a microwave oven if the door does not close firmly, is bent, warped, or damaged, or if you somehow make holes in the door. Although the microwave helps us heat food, it certainly requires an upgrade to utilize the potential of electromagnetic waves for cooking. In the new generation of microwave oven, the magnetron has no place, with RF circuit expected to take its position. For more information about how future smart microwave oven works, subscribe.